Ah.
Okay, let's continue. Okay, start looking at communication systems in application. There are different types. Mostly want to reuse Ethernet communication because Ethernet is very cheap, but we have some issues with the performance of Ethernet in real-time applications. So one specific part that we did was EtherCAT, and EtherCAT is a field bus system that allows us to use Ethernet for real-time applications. And we had like a structure that looks like a tree, but in reality it's a data package that's traveling in a circle until it's coming back to the master. And the idea of EtherCAT is to have data processed on the fly, so it just passes each and every sensor and actuator in the field. And while it passes the sensor and actuator, basically the data is exchanged, so the input data stays in the output data is extracted to be used in the sensor and actuators, and the input data is passed back to the master, so it's added to the telegram and is received file data. And for that we have to build up these telegrams, and most of the time we have to do that actually offline. And that's what we did in the lab as well. That's what we didn't do in the lab because we had the hardware, so we were scanning the hardware, but in reality we would not scan the information from the device itself, but we rather have a device description, so you can actually add a slave to the system before it is actually available in your system. And you can already do the parameterization, and you can do all the necessary stuff to keep to get the device up and running without actually having it. And then when the real when you transfer it to the real system, it's just a comparison whether the real system is equal to the system that you configured. And if it's the same, then it's just the system starts up. So here we have that EtherCAT slave structure, and we have these information devices that are processed. So when you build a slave, you can actually build a slave an EtherCAT slave as a mini project, but it's programming, so it's a C SDK, but it's not so difficult actually to build these slaves, because the only thing you have to create is like you have these EtherCAT slave controllers, and they are like a fixed chip that are able to pass on the information, so and extract information and add information on the fly while the data is passing. And the only thing you really have to do is like configure these slave controllers, so you have to configure the information. And because it's only a data signal that is passing, these EtherCAT slave controllers, they are very inexpensive and easy to make. So they use standard Ethernet PHYs So the physical engine is a standard Ethernet engine, and then just the bridge from one file to the output file, that is a simple logic extracting information. But you have to install that special type of hardware in each and every slave, and you have to create a chain, so there's some restriction on how you can actually build up a network. You're not as free as you would be with a standard IT system. And one thing that EtherCAT actually did quite successful, there was other standards that are available for the automation industry. So first we have standard Ethernet. So there's a stack that is able to just pass on standard Ethernet traffic. So that's why standard Ethernet over EtherCAT is still working. Then you have additional things like file system, bootloader, so things that allows you to modify the firmware and transfer files. You could use FTP as well for that. But so this is like standard Ethernet with your normal internet traffic. This is some additional library functions that you can use to interact with your device. And on this side here, there you have the interaction with the device itself in terms of real-time data. You have the process data that gets exchanged each and every cycle. And then additionally, there's two standards that are actually included in EtherCAT, and they just copied the Sercos standard, and that's why Sercos is actually not in the market anymore, because you can just use it over EtherCAT, and EtherCAT is more performant and cheaper. And Sercos was used for all the drives in the automation industry, so connecting hundreds of drives together in an application that's possible with Sercos. And then you have CAN-open that comes from, the CAN bus is from the automotive industry, and then there was a standard used, the CAN-open standard used to make CAN accessible in the automation industry. And they just integrated the two standards, and they're kind of old Sercos that CAN-open, like from the 70s, and yeah, still working integrated in these Ethernet devices. And yeah, that's basically how EtherCAT was able to ramp up very fast, because we just copied technologies. Then there's one additional thing that is important in the automation industry, and that is safety. And safety was included in most of the Fitbus systems, but yeah, basically there's one trick on how to easily implement safety. Here you have the standard application, just standard data exchange over EtherCAT between the devices. And even though there's like the correction of data, and you find out that telegrams are missing, or that they got notified and so on by default on the Ethernet, there's an additional safety layer, because yeah, that's not enough for real safety applications. And for example, if you have a emergency shutdown switch and you have a drive, then usually they were connected directly, but when they connect via EtherCAT, then they have an additional safety layer, and the drive basically checks, like each and every cycle, it checks whether the drive, whether the button is pressed or not, and if the button actually doesn't answer, it assumes that the button probably is pressed, and then it executes safety function by itself. So there's just an additional logic that you put on top for executing safe functions if the other devices are not in a safe state. And doing that, so having this additional layer on top, that makes the communication just as a so-called black channel. So you assume that the communication itself is not safe. You do all the safe the exchange, so addition, and you like cross-check all the data and everything between the applications. And as long as these black channels are transmitting data correctly, that will work, reliable. And if they do any mistakes, then of course the safety layer would be activated and executed. But that allows us to like use normal safety, normal communication systems and add safety to that. And Ethercat also didn't invent that. That was actually copied from Profibus. So yeah, if you are a protocol vendor, most of the time it's actually good to like just copy efficient other solutions. And we had the same on the opposite way, like Profinet in the end, my former professor, he went to Beckhoff and he was working on Ethercat and Ethercat safety, and then he went back to Siemens and like incorporated all the knowledge he got from Ethercat into the Profinet, and then Profinet evolved a lot, and now he actually moved back to Beckhoff again. So yeah, they try to copy a lot of things that isn't. That's why they, yeah, if it's not patented, they can actually copy a lot of the ideas. And I think that's what you basically saw on our in our lab. You have the device screen there where you can actually scan for the devices. And here you have the Ethercat master. And the Ethercat master is just a normal Ethernet port on your PC. But it needs to have a dedicated Ethernet chip, otherwise it's not real-time capable, so there's only like some Intel chips supported and other chips are not supported. And then you have the terminals, and each of the terminals have like a head station where you do the translation between the Ethercat on Ethernet standard to the low voltage signal, and then you have the Ethercat passing through the terminals, and then it's reassembled to a Ethercat frame at the end. And that's also the reason you see that like here you have these terminals, and at the end there's always a termination terminal. But actually that's just the round trip terminal. So the Ethercat frame comes from the master, gets translated to this low voltage differential signal in the first place here, then passes through all these Ethercat devices as single devices, and they have all their dedicated address. And then it needs to turn around, and that's actually what this module is doing. It's just electrically connecting the transceive and receive line, and then the signal goes back through all the terminals to the beginning of the tree part, and that is, in our case, it was just a single cable, so it went back to the master. We can support communication speeds or cycle times of around 32 microseconds, and that's also the limitation for high-speed machining devices. So if you have like a milling device or whatever, and they are very fast ones. They travel at 1 meter per second, 1 meter per minute. No, actually they can travel in fast forward, they can travel 1 meter per second. And that would be, if you had a resolution of a micron, you would have 1 million steps per second, and you need a very fast cycle time actually to be able to control these drives in the end. And then, if you have 1 million steps, that would be 1 micron per step, and then you already have you missed 31 steps, so you control cycle is up the next time. So it's really time critical if you want to have high performance milling processes to get a fast cycle time. Not in the oil and gas industry, minutes is okay. Okay, that's so far for the communication to the lower levels. Let's see, Profinet is actually very similar. It's just a different, technology running on Ethernet. The difference is you can use standard Ethernet up to a certain performance level, speed level, and then you actually have to switch to a higher, to a dedicated hardware, which in the end is much more expensive than the Ethernet hardware. So it's a trade-off, in the slow moving stuff you can use standard hardware, but for high-speed communication you use a dedicated, more expensive hardware. And let's see what they actually did to improve the speed of Ethernet to match it with the speed that we need so industrial Ethernet to match the speed of normal applications that we have. Okay.
It is well suited for even the most demanding applications. Those that require the highest efficiency need the shortest possible cycle times. Shorter cycle times allow the manufacturing environment to be faster, increasing productivity. One method that Profinet employs to increase speed is known as fast forwarding. Every Ethernet frame has an ID built in that tells a node if the packet is intended for it or another device on the network. By moving the ID at the beginning of the frame, it allows the device to decipher sooner whether it should process the data containing the packet or simply forward the frame. The second technique used by Profinet is called dynamic frame packing.
Okay. I don't know if you ever saw that, but if you buy a normal router by the time now, so about 2005 or 8, they started fast forwarding, so even if you buy a normal device at home, that supports fast forwarding by now, because it is also important, latency is also important for the gaming industry and telephone systems and so on. So that actually came from Profinet and is now the default of Ethernet, so in the Ethernet standard. So they basically just move the data early in the frame so that the electronics can decide earlier where the frame has to go next. Otherwise, you have to read the heart of the frame and you wait until you decide which route you have to take. And the next thing then is dynamic frame packing.
Instead of sending individual frames from each node, a summation frame that contains all data for devices in a line. Then, the process data is captured on the device, minimizing the size of the remaining packet.
Okay, dynamic frame packing, that's something you don't have in normal Ethernet. So we have these frames, and usually you have single frames, and then we have, like in EtherCAT, we have the frame as a whole traveling through all the nodes, and that was patented. And when my professor came back to Siemens, he found out that the hole in the patent is that you start with the whole frame, and then a part of the frame actually already returns at node 1, because it's already, the data from node 1 is already processed, or you wait in node 1 till the data comes back, and then he like has a package that gets smaller and smaller over time. It just contains the information for the remaining nodes. So here you have the 3 nodes, and then you just have 2 nodes remaining last node, and then the package turns around and collects the information back. So basically we stole the idea from the internet and found a loophole in the patent to make that possible.
Implementation increases bandwidth dramatically. Since Profinet is an open technology, standard TCP/IP traffic is permitted to coexist on the same wire as Profinet traffic. These large TCP/IP frames are split into smaller frames. This allows more Profinet data to be transmitted at increasing speeds. In all, between these 3 techniques and those described in our 4-part series, cycle times as low as 31.25 microseconds can be achieved. Incredible.
So that was the next thing that they had to do. The TCP frames, they can be very large, the standard Ethernet frames, and that's when you actually need dedicated hardware in the end, because that is not a standard Ethernet communication anymore. You split up the Ethernet frame in multiple single packages to have more Profinet frames in between, and basically in the Profinet device you then split up what is relevant for Profinet, and if the Ethernet package leaves the Profinet environment, it gets reassembled at the end and then transmitted as a huge frame. Because like the biggest frames in the TCP IP world, they take around 120 microseconds, so about 4 times more time to actually be transmitted. And that's why they get fragmented. And also all these Ethernet types, when you look at the Ethernet specification by now on Wikipedia, you'll see that like EtherCAT and Profinet and so on, they have dedicated IDs reserved in the Ethernet frames, so that the hardware of the Ethernet can actually identify this package and then prefer that. That's like you have traffic shaping for in a normal switch as well. If you have like traffic for TV or whatever, then it's preferred compared to the file transport or whatever. So that's why actually the automation industry, they did a lot of changes in the end to the Ethernet world, and you see that in the specifications as well, and that's why now Ethernet actually can be used as industrial Ethernet for our applications. Okay, that was the lower level connectivity. There we have mostly the need for high-speed connections with low latency. And now we have the connectivity to the upper levels, to the higher levels of the factory, and that is machine-to-machine communication, but also machine-to-plant communication. So all the connection to higher levels. Okay, if we look at process control information, that's like the legacy, how it used to be. you see very old Windows systems like Windows 3.1 and Windows 95, which was developed in 95. And that was like the first attempt of integrating the IT and the process components, so the plant itself. And what they do is, like, you have a cut here in between, you have the business management, and then everything below somewhere is a plant highway, where you have your process control. And the two networks, they were actually always splitted by some machines attached, but not like that you could actually switch from one network to the other easily, because they were also different technologies. And if you wanted to have a client application working with information from this device here, you had to go through a translation tunnel in either of these machines, and that was actually a challenge, because there was no connection between those two networks, so you need like translation software installed here. And the main thing where it started was these controllers, they don't have history, so everything in the lower levels can only have, for example, if you have a temperature transmission, or pressure, you only get the current value in the control loop, you don't get the history. And if you want to have a trend chart for your pressure or temperature, you somewhere have to store the data, and that's why you have these collection servers, and they started actually collecting the data from the field, so reading the control values each and every cycle and just storing them somewhere, and then making them available for client applications, so that you can see the history. And that was the beginning of how can we actually integrate the factory with the shop floor with the rest of the factory or company network. And the main thing that they identified in the end was that they had three main use cases. And the first use case was so-called data access, so that's just access to information on field level device. BA is data access. And that is to data of field level devices from higher levels. And then they had a second use case that is historical access, so that is like the trend charts and everything. And then we have a third channel that is alarms and conditions. It used to be alarms and events. And the main thing is, like the IT industry, they work with events and not with reading data cyclically. So they want to have a trigger event over temperature or whatever, and that is then generated by these alarms and conditions servers. So we had dedicated server architecture for example, for historical data, and then we had another server for data access, that we had another server for the alarms acquisition, and you could connect to them and use their services and to interact with the lower level parts of the field. And to solve that, they created a technology called OPC. And OPC is coming from the SCADA systems. We have a SCADA system that's supervisory control and data acquisition. We'll have that on the next slide. So we want to monitor what's going on the field level, and for that we want to have a standardized interface to the field, because the client here wants to monitor information from a certain point in the field, and he doesn't know how to communicate via field level protocols or whatever. He just wants to access the data with standard IT technologies. And that's where this OPC UA standard comes into place. So we have like a split here. The lower level, that is vendor-specific communication. Vendor-specific communication, and down to our PLC or DCS or whatever it is. And on top of that, we want to have a standardized communication that is vendor independent, and that is this OPC communication. And that is vendor independent. And the idea is we have this cyclic communication on the PLC level, and we have a server in between that allows us to be connected via standard IT technologies, and he just initiates the communication, the client to the server, and then can read, write, monitor, process values, and execute commands in the field. So the first thing we do is we initiate the communication. To the field, and then we read, write, or monitor, and process values. And there's also the possibility to execute commands. Usually we also have functions in the field, and we want to be able to execute them as well. And when the client initiates that communication, then we have to do something on the server side for that. So the server on the other side reacts to client commands, reads and writes. Then we have this cyclic reading of process values, because the process values, they are just cyclically exchanged each and every PLC cycle, and they have to be either cached or somehow to be available for the rest of the system. So on the lower level we have cyclic reading. Of process values. And we need to monitor process values. And that's actually monitoring changes. And changes, they then create events because like the IT world is event-based and the PLC world is cyclic. And we might want to store the history, so we want to store historical process values. And OPC, the technology itself, then basically the transfer technology between the lower and the higher level in your plant. And it was first developed around 95, maybe a bit earlier, but the first systems were around 95. And you had these SCADA servers, so these supervisory control and data acquisitions, and they collect all the information via these data servers from the vendor-specific systems. So here we have vendor-specific field buses and so the PLCs or DCS systems, and then somehow we need to make a transition to the normal IT technology, and there a vendor builds an adapter to create data access to the cyclic information, and then for example we can read these data cyclically, make that accessible, and if we store that cyclically in a database, then we have historical data access, and we can create alarms if something is out of range or whatever. But yeah, that's the thing that the SCADA system is actually doing. So it has normal IT technology, a database to store values, and then some logic to create alarms and events. And the technology itself, I always said it was invented somewhere in 95. There was mostly Windows technology. There was few other systems, but it was a very dominant field by Microsoft. And Microsoft had a technology called OLE, Object Linking and Embedding. Probably you've never heard of that, but maybe you have used it already. So object linking and embedding is, if you are in a, for example, you have a Microsoft Word file and you are writing raw text, and then you create a table in Excel that is integrated into your Word file, that is, you link an object from another technology inside your document. That is object linking and embedding, so something gets embedded into your document. And that's, for example, not possible if you run Word on this machine here. It doesn't have object linking and embedding, so it's not possible to actually do that. And the idea of this technology was that the Excel document could even be on a different machine, somewhere in the network, and it then was found via a technology called COM-DCOM, and the information that was transmitted into your document. So you could have like an Excel file that runs or that lies on a server, and the Excel is executed on that server, and you embed that into your document. And there could be multiple users actually embedding that. So that was the idea behind that, and that's why OPC was OLE for process control, so using that technology for process control. By now that technology of course is gone, and OPC was called Openness, Productivity and Collaboration, and then I don't know the current naming. But basically it was all done with Microsoft technology. So OLE is a Microsoft technology, and it uses Common Decom in the Microsoft world to actually do the communication. And still the backbone in Windows itself, if I say applications are communicating with each other on a low level, they can use Common Decom in the background in Windows, and it's a very performant data exchange model, but it has a lot of flaws in terms of it's very easy to mess up the program and then create common devices that actually don't disappear again. Microsoft never thought through all these use cases that are actually that come up when you have distributed software, and they never really like implemented that perfectly. That's what Open Standards then later did with our upcoming internet world. There we had applications running on multiple servers. And so even though that is still available somewhere in the back of Windows, I think Microsoft is the only one using it really while programming. And as a user, you don't want to actually use that directly because it was so easy to make mistakes. Windows technologies are kind of bad anyhow because there's no Windows running on the PLC. So the PLC was not able to integrate these data access servers, and then we had all these flaws with the distributed communication. So there was a time when they said, okay, we have to like get rid of Windows and change our base technology on how to exchange information, but like the overall use cases that I identified, they are still the same. They wrote down what was necessary about 30 years ago, and that's still valid. It didn't change. So what they did was like they had to think about how do we actually evolve this technology, the OPC technology, and that's how they started with OPC data access, and then it had this historical data and the alarms and conditions, and that's our valid use cases, but based on OPC, was based on Microsoft technologies. And then the internet world started, and Microsoft technologies didn't work well in the internet, so they started to create something called XML data access, which kind of worked, but is terribly slow. So it didn't really work for the automation industry. But it was the first thing where they actually could send data over the internet and pass through firewalls and so on, because that's not possible with technology. It was completely proprietary, and you would never actually pass any firewall in the internet. Then they had some additional use cases, like this is the main use cases, and then they said, okay, we want to have like better PLC to PLC communication. Still, actually, it's just on top of data access, because like you have data from one PLC accessed by the neighbor PLC. And then with the internet technologies, we had to think about security and we also actually, then they also like thought of, okay, if we have data access, we can actually call whole programs, and that is kind of interesting because that makes, if you specify, if you implement that completely, you don't need proprietary development environments for a PLC anymore, because you can like create any program with standard OPC technology and then just download it to the PLC and execute it there. And batch programming, that is important if you have like a recipe and you want to produce, I don't know, milk yogurt and whatever, and you change the recipe over time, because you always want to create different types of products. So it got exchanged over time a little bit, but the main thing is those three standard use cases. Okay, so that's the problems is why actually the OPC Classic evolved, and the main reasons were that we had this DCOM technology in the background for communication, and that was just a Microsoft standard, not available anywhere else. And even Microsoft was hiding that in .NET. So the .NET technology is hiding, encapsulating that because it make, they try to make it easier to program that. So .NET is a unique technology, and that is used for web services. And also that is not the main part that is used as a technology in the internet. So it was a wise decision to get rid of DCOM and also the predecessor web technologies like .NET. Then DCOM actually is very hard to configure. The DCOM configuration is difficult and completely intransparent. Like in ADB, when I was configuring these clients, we had like a manual with 120 pages, and you had like to go for each and every page and do all the clicks, and then in the end it didn't work, and then you went through 120 pages again and did all the clicks, and if you miss one, it just didn't work, and you never knew why. We have big security issues with that. Security problems. With DCOM technologies. So it's security by obscurity, that's how Microsoft worked for a long time. Then there's no firewalls. Possible. And in the end, we had very bad performance. For real-time requirements, so meeting real-time requirements. And that's why we somehow had to evolve to a new technology. And yeah, get all the benefits that were available in the new internet world. So they created, around 2000, they created a vision of OPC UA. So the OPC Unified Architecture. And the use cases are the same. We still want to have data access, historical data, alarms and conditions. But we don't want to just work on a single device. We want to be independent of the hardware and then work on any type of device. So whether it's like our PLC device or a laptop or a larger server, that's like where the laptop and the larger servers, that's where the old OPC devices were working. But we also wanted to, and desktop, but we also wanted to work on phones, and also very small devices. So by now, you can work on devices that have just a few kilobyte of RAM and up to very large mainframes. And then we have this internet, so that was platform independence to work on all that. Of course, we have to take care of security, otherwise the internet world is not really open for us, or at least not safe. And then there's a last part, and I don't know, does anybody know MQTT as a data exchange technology? It's very often used in the IoT world, and MQTT is like the simple version of OPC. It came out later, and the main difference is actually that MQTT doesn't have an information model. The rest is pretty much the same by now. And information modeling means that you are able to define data structures of your plant and model the data of your plant. And if you do that, it's like an additional overhead you have to do. But on the other hand, once you have structured data and data that has meta information, you can do things like you can Google for data in your plant, because if you search for information in a plant, you need to know and identify the elements, the data elements, and that's only possible if you have additional information about how the data is structured and what it actually means. And that's why information model is, on the one hand, very powerful. On the other hand, it made the technology a bit more bulky. And now we have a mixture of like the very light frame version with MQTT, and on the other hand, OPC if we need this additional information model. So that's where OPC Unified Architecture came into place in around 2005 or whatever, and then later was incorporated in these Industry 4.0 standards and became the standard of Internet of Things, or Industrial Internet of Things, and machine-to-machine communication. And then the automation industry found out that the IT industry liked OPC UA and how it was working, but then the IT industry is moving much faster, and they started with RBE, the lightweight version of that as well, and they created MQTT, and the automation world actually couldn't follow that anymore. By now it's more IT driven than automation driven, because it's just used for all these IoT devices and IIoT devices. On the other hand, it's good that the technology actually evolved faster than it evolved before. So let's make short. We can go to See?
What is OPC? OPC UA is the open standard that specifies information exchange for industrial communication, particularly on devices within machines, between machines, and from machines to systems in a convergence of IT and OT. It can be used with any software platform, Windows, Linux, Mac, Android, well, you pick one. In this case, OPC UA is scaling from minimal embedded controllers to massive cloud infrastructures, even mobile devices. OPC UA is equally suited in a closed network or utilized via the internet. Don't worry though, security is baked into the protocol for access control, authentication, and encryption. Because of its flexibility, OPC UA has been widely adopted in industries like automotive, food and beverage, oil and gas, energy and utilities, packaging, building automation, and so on. So, as manufacturing moves into the industrial Internet of Things Industry 4.0 realm, OPC UA is already poised to fulfill requirements.
Okay. So OPC, even though it's like they said, it's widely adopted. It is widely adopted and they use it, but it actually took a very long time. So the first PLC from Siemens that was supporting OPC is now, I think, 6 years ago. And if you look at the timeline, it was like 15 years after they actually decided on moving to OPC, it was available in the system itself. So by now, yes, all these systems support OPC UA, but once you are in older machines, 10 years and older, most of the time you don't see modern OPC, but rather classic OPC, and that's why you still have these old windows there and you can't update them. Yeah, that's how it works in the automation industry. Okay, that's the thing, like the basic benefits. We have all the stuff that we need for the communication in the internet, but one additional interesting thing is this information modeling, to be able to model complex data and make meta information available about your plants, and the rest is basically you just have a Windows independent implementation of our classic use cases. The performance is also quite good by now, so we have like in the oil and gas industry, we had about 300 to 400,000 data points, and they were exchanged in 10 millisecond cycle time between the servers, and that actually went quite well. What we used OPC, for example, was that we had a simulation model of the whole plant, and then you could actually, instead of connecting the DCS to physical hardware, you connect it via OPC or to your simulated system, and the performance was good enough for the system actually to work in real time. So it's really a performance way of communicating and what the industry in the end needed. And now, because we have OPC UA on all the levels and we use standard internet technologies, we can actually also overcome these firewalls, and we can seamlessly integrate into the hierarchy of a company. And we could also then access cloud services and so on, or the other way around. Cloud services were able to access information on the shop floor. Microsoft had an Azure demo not too long ago, maybe 8 years or something like that, where they had like the first thing where you could switch on I think it was a hairdryer or whatever, and they had like a plug and you could switch it on the Azure cloud. By now it actually is integrated in most of the cloud services by default, and also things like enterprise resource ERP tools like SAP or whatever, they have standard plugins for OPC UA, and then you can just access information in your field, and that makes scenarios possible where you have, for example, you have a light switch and it detects that it actually is dirty and you need someone to clean the light switch, and that means that you have to actually use a resource in the ERP system and write out a task to a maintenance worker that goes in and cleans it, and then someone has to say, yes, I cleaned it. And now the light switch can by itself communicate up to the ERP and say, I need some maintenance, and if the maintenance is done, you can actually also say, yes, the maintenance was done. And that wasn't possible before on an easy way, and now it's at least doable with less effort. And then we have OPC UA specifications. I don't want to look at like the core specifications or anything, but you have this part of information modeling, and they try to get rid of the problem that we have a specification that is dependent on a technology, so they have an independent description of what OPC UA is doing, and then they have a mapping on a technology because we have to implement it somehow. And then you see the standard parts again, where you have the data access, alarms and condition, historical, and additionally by now these programs. And then we have some additional specifications on how to discover OPC UA server or aggregate them to a larger OPC UA server. And you also see that it's a standard IEC standard by now, and so it's an open standard that can be implemented by any vendor. We have the same possibility to communicate. As with OPC UA, we have this client initiating the communication, and then the server needs to answer. Actually, the OPC UA doesn't really care anymore whether you are a server or a client. You can be both at the same time, but still like to open as a client, you open a connection to a server, and the server responds to your request, or if you requested to monitor some data, it can publish notifications. But any OPC UA device can act as a client or server at the same time, depending on whether information is subscribed by the device, then you are a server, or whether you read some information from another device, then you are a client. So what is the information model behind that, and why is that actually important? So we have our standard services allowing the OPC server to request and response to messages and publish notifications. So that is the standard way, the same as the Ethernet, the internet world is actually doing that. And so it's a publisher subscribe and a read with the response message type of interface. And then if you look at the server behind it, you have this UA address space, and that is a set of nodes, and the nodes is data, and these nodes are then mapped to real objects. We're gonna see that later in an example. And if you want to like monitor information, you can monitor nodes and therefore their data and subscribe for any change, or you can request a read or a write to any of these nodes to change information. And this address space actually is then what they have specified as a layered address, as a layered system. So we have our transport, meta and base services, that's like the core of the OPC world. Then we have on top of that, we have our data access, historical access, alarms and conditions and program, and that's the standard access to our node system. And on top of that you can have collaboration models, and on top of that you have vendor specific extensions. What does it actually mean? The problem is when you have a factory and you create each and every factory individually, then you have to integrate it individually by hand. Maybe AI will help us to actually do the integration in a faster way in the future, because we can actually analyze semantics better. But by now we have these collaboration models to solve that task. And these collaboration models, there's where vendors actually agree on one type of data set for their machine. And the first data set that was a collaboration model was the so-called Weinstephaner Standard. That's for the Germans here. Weinstephan is a brewing company, and they had like brewing equipment, and they just wanted to standardize the information that is coming from brewing equipment to like monitor the process. And they didn't want to always manually find out where the data is. And that's why they created this collaboration model. And Weinstephaner Standard actually was created for Weinstephan. It's a very small brewery actually. But it was adopted by the whole industry. It's now, you can buy a brewing equipment according to the Weinstephaner Standard and go. And that's then the information gets also very easy to be integrated in your SAP system or whatever, because then you just plug in a OPC UA connector, and then you say the information follows the Weinstephaner Standard, and then that's it. It knows where to find which type of information. And you don't have to connect anything manually anymore. So collaboration models, they are very powerful. You have the same in the packaging industry, in the pharmaceutical industry, and so on. And that is, it makes the connection to information easy, and you can also monitor multiple sites, different sites on the world, and integrate them into your company without a lot of effort. Vendor-specific extension is then when you need something additionally, but then once you use a vendor-specific extension, of course, then you have to do it as a manual process. So how does it actually work? Like you have these collaboration modules, and they are created out of objects on a low level, and these objects have variables and they have methods. And if you look at the object, then you can read and write a variable, and you can get notifications for data changes. So this is just normal access to information. And a method, of course, a method needs to be invoked, and then the method is executed. And the whole object itself can create event notifications. So here you just have the data changes, and for example, the object itself can create an alarm or whatever, and create an event that you can monitor. And objects have references to other objects, so the object one was just an object-oriented view of your real-world machine structure and processes. So this is like the object is a set of nodes, because it's just the objects connected to other objects, and we try to represent your physical world. And in a object-oriented world, you have classes, so object templates, and these are these node classes. And if you create an instance of it in your model, then it's the object instance of a node class with attributes and references to other nodes. Did you have any object-oriented programming in master? Yeah? Object-oriented model. Not sure.
It's not much we can pick up finally, or
And that's the complete.
they didn't attack.
Yeah. Yeah. OOP, object-oriented programming. So the same here applies here. You have
Little, maybe Python, but
a structure, a template structure, and you create an instance of it by creating a. So you use the classes as a stamp, as a template, and you create as many instances as you want using that classes. And there, it's the same. I don't actually know why they did it. They have like they have their own their own notation on how to describe these models. They could have just, in my opinion, relied on what's in the IT industry, like they have UML, and it actually perfectly describes object-oriented models, but they decided to have an additional representation notation. So we have like always object, variable, method, and they have types. So, and then they get these shadows, so you have an object type, and that gets instantiated as an object, and you have a variable type, the definition of the variable, and you have the real variable with a physical value. And of course, an object has one or multiple variables, and a variable has a certain data type, and an object has usually a reference to other nodes, and a variable has also a reference to its data type and to its object. So they just are connected in an object-oriented way. And then you have views. We see views later. It's different views on the same data, depending on what your focus is. And then you have these references, so the connections between, and there's typically these in the OT world, OOP world, you have a class, and the class has internal variables, and the external variables usually are called properties, and they can be read or so you can read or write them. And then a class probably has components, so it aggregates other objects. And it could have subtyping, and definitions, so it depends on the definition and has it basically gets how do you say it's erbt in English. It gets information from another type, so it aggregation is just to get it it inherits, that's the thing, it inherits information over time. But anyhow, this is just like to build up the structure of the data, and I think if you just read the names as they are, it's somehow understandable what that means if you know something about object-oriented programming. References, they have a direction usually, and so they can be symmetric or asymmetric. Most of them are actually asymmetric, just in one direction. And what does that actually mean? So if you have an object model, then, for example, you have a boiler, and the boiler has a pipe and a drum and another pipe, and the pipe has a valve and a transmitter for the flow, and the drum has a transmitter for, I don't know, the level, and then you have another pipe and that has a flow transmitter as well. So that's like the hierarchical structure of your machine with all the elements. A boiler has a pipe, has a drum. And on the other hand, you have a functional structure, which is just a different view. So you probably have a function to control the level and to control the flow, and an overall controlling of the whole boiler. And so it's just, here you have the functional model in terms of a control unit usually has a set point and it measures something and it has a control output, and you see here the same again. It has a set point and measures something, and depending on the set point controls the output. And then you have like the overall controller of the whole boiler, and that has certain inputs and outputs. So what you can do is like you model the information of your plant in a hierarchical manner, and you can match any other views depending on, here we have the hierarchical view and the functional view. You can create any other view you like as well. But that's why this modeling, if you have like a standardized model, and you can just use something like the Randstedter Standard, then you don't have to do all this modeling, and the data is structured always in the same way. That makes life easier, and otherwise you have to do all these connections yourself. Maybe let's look at one last example where you have a motor, for example. The motor has a type, so here you have the type, so the definition and a type. Motor type has a status and a configuration, and it has the method start and stop, just as an example. And then you create the instance, the real motor, that is related to some of the motor. In this case, it's just motor 1, and yes, you can read its status, and you can start and stop it by invoking these methods. And that is then the way of how you can use the type definition as a template for multiple of the same instantiations, so of the same different motor types because you probably have multiple motors in the system. This modeling actually, there was around 2000, there was something called Profinet CDA, Profinet Component-Based Automation, and that already had all these ideas, but it was baked into the Profinet specification, which is a communication description, doesn't really fit there. That's why it wasn't used, but with the Profinet CDA, you could actually do all these machine connections and modeling already. And I used that as a student and thought that was actually quite convenient to like plug machines together in a standardized way and so on, and then that completely disappeared, and also the possibility disappeared, and now it's back again with OPC UA that can actually do things like that. So the automation industry is by far not as advanced in data structures and so on as the IT industry. We are just, we have simple machines and we just had simple problems, and then found out that if you don't apply a standard and a good data modeling, you end up doing everything by hand, and you do everything again for the next machine and so on. That's why that is really a step forward. But on the other hand, if you have a very simple IoT device, it's probably just too much that you have to do, and that's why you have also this simple MQTT where you just read and write data and you don't really know what the data means. It's just like, give me value 1, and then it says, well, the 1 is 100, and with OPC UA you know that this value is part of a motor, and it's actually the temperature of the motor, and it has degrees Celsius, and so on. So just depends on how much additional information you need, whether you want to have this complex modeling or just simple data values. Okay, that's it for today. 9:30. Thank you very much. See you next week.